Okay, so this is the multiple choice questions on refraction, diffraction and interference patterns. And before I start, one thing I'd like to do is just point us in the direction. Remember always you need to have your data constant and formula sheets. The waves equations are all given on the second page. Here we're looking at, so those equations at the top, that was for the first multiple choice part, which was just on waves, progressive and stationary. Here we have for refraction, diffraction and interference. This is the equation for the diffraction grating. Sorry, I beg your pardon, for the double slit experiment. Interference, this is the equation for the diffraction grating. And here we have the equations for the refraction. Okay. Now, one equation that's not given on your constant sheet is the equation for single slit diffraction. You're not required to know this quantitatively, you're only required to know about it qualitatively. But I think it's useful to know the equation, which is the sine of the angle between the center of the slit and the first minimum is equal to the wavelength over the slit size. Okay, whereas in the case of diffraction grating, this is the angle from the center of the diffraction grating to the first, in this case, the nth order, the nth bright fringe. Okay. Now there are three scenarios that we want to look at. Diffraction happening at a single slit, diffraction happening at two slits, that's the Young's double slit experiment, and a diffraction happening at many slits, and that's the diffraction grating. So diffraction is the spreading out of a wave, and interference is the pattern that's formed from two or more waves that are superposing. So, and hence we get bright and dark places where we get constructive and destructive interference. Okay, now, so let's just remind ourselves what diffraction is. Diffraction is the spreading out of a wave. Now, this is something that in the AQA's A-level curriculum, you do not need to know this quantitatively meaning with numbers, working out, using an equation to work out an answer. You need to know it qualitatively. So what we see is here we've got a waves on water or ripples, and they're passing through a gap, and at the top we see here that we have a large gap compared to the wavelength given as the distance between the crests, and at the bottom we've got a much smaller gap, much more similar to the wavelength. So what we find is with the at the top, the wave passes pretty much straight through. There's a little bit of spreading out to the sides, but there is a narrowish beam of waves coming through the gap, whereas when we've got a much narrower slit, the beam spreads out, so the beam coming through the gap is wider, and by beam I mean this area of the waves. So qualitatively we can say for single slits we get this sort of pattern, and we can say that the central maximum is brightest. There are fringes on either side. So the central maximum is brightest and there are fringes on either side. Those fringes are not as bright and there are dark fringes in between. The central maximum is much wider than the less bright fringes to either side. And if diffraction is increased, that is, if there's more spreading out of the wave, which is what we saw in this case, here we have more diffraction, there's more spreading out, then that central maximum becomes wider and less bright. If we put monochrome lights through the slit, we get a bright central maximum with fringes on either side, and if we put in white light, then we get a central white maximum with the spectrum of colors on either side, and we see that the red is moved further away from the central maximum than blue and violet. Okay, now I said that you only need to understand the single slit qualitatively, the single slit, I beg your pardon, diffraction qualitatively, but it is useful to know the equation. Now, this is something that we met in lesson. I don't propose to go through that. I'm just going to talk about this equation. So this shows the angle between the center of the slit and the first minimum. So it's telling us about the width of that central bright maximum. So the sine of that angle is equal to the wavelength divided by the slit size. So we're saying that if we have a larger wavelength or we have a smaller slit, then we're going to get a larger value for the sine. And obviously you can also see that if the wavelength equals the slit size, then we would get the sine of the angle is 1. In other words, the angle would be 90 degrees, which would give us the maximum amount of diffraction we can have. It's useful to know that equation because, although it's not given in your equation sheet, because it just allows us, when we get questions that ask what would happen if we change the light from blue light to red light. Changing from blue light to red light means that we've increased the wavelength, and we can see then from the equation what would happen to the width of the maximum just by using the equation. The second situation is the double slit experiment. Here's where we've got light from 2 slits, and remember we've got the pattern formed by the double slit is superimposed on top of a single slit diffraction pattern. So this is the central maximum for the single slit pattern with its fringes on either side, and then on top of that we have the fringes formed from the double slit interference pattern. And again we have an equation that I'm just going to move on to, which tells us that the separation of the fringes, which is W, is equal to wavelength times the distance to the screen divided by the slit spacing, and that equation is given in your equation sheet. And then the third equation that we need to know is the diffraction grating. What we see is that as we increase the number of slits, that we get more and more points of light rather than the light being spread out. So if we go for a diffraction grating, we have this equation. It says D, which in this case is the slit spacing, multiplied by the sine of the angle. That's the angle between the center of the diffraction grating to the nth bright fringe, is equal to n times the wavelength. And here again, as I showed before for the single slit, this is what happens with a monochrome light and white light for the double slit pattern, and likewise for the diffraction grating, where we have again the at the top we have the monochrome light going through the diffraction grating, at the bottom we have white light. Part of the table is looking at the width of the beams. So this is really about diffraction. The objects have been diffracted, the beams have been diffracted by objects of the same size. So we're looking at which is going to spread out more. And we can remember, and this is where it's useful just to have that equation, even though it's not on the curriculum. We see that the sine of the angle, in other words, how much the beam spreads out, depends on the wavelength. So if the wavelength is greater, it means the angle is greater, which means the beam is wider, it's more spread out. So the electron wavelength is greater, which means the beam is going to be greater. So the answer is A. Question 2. A diffraction pattern is formed by passing monochrome light through a single slit. If the width of the single slit is reduced, which of the following is true? Now again, this is normally what we say. We think of this qualitatively, but again, we can use our equation to help us. What we're saying is that we're reducing the width of the single slit. So what's going to happen if we reduce that? Then we make the sine of the angle increase, so the width is increased. So by reducing the size of the slit width, we are going to increase the width of the central maximum. So that means it's not going to be A or D, it's going to be one of these two. If we increase the width, that means the beam is spreading out, so that means the overall intensity is going to decrease, so our answer is going to be C. Question 3. A light source emits light which is a mixture of two wavelengths. When the light is incident on the diffraction grating, it's found the fifth order of light of this wavelength occurs as the same as the fourth order for the light of the second wavelength. If that is this wavelength, what is the other wavelength? Right, okay, so remember, we can look at our sheet. It tells us what the equation is. So we've got the sine of the angle is equal to n times the wavelength. Now what we were told is that we've got the sine of the angle is equal to 5 times the first wavelength, and that's also equal to 4 times the second wavelength. So that means the second wavelength is equal to 5/4 times the first wavelength. The first wavelength, we're told, is 480 nanometers, and we just need to put that into the calculator. We've got 5 divided by 4 multiplied by 480, which gives us 600 nanometers. So that's answer C. Question 4. Comparing X-rays with UV radiation, which is the following? Well, X-rays, so the wavelength of X-rays is less than the wavelength of UV. The frequency of X-rays is greater than the frequency of UV. The energy carried by X-rays is greater than the energy carried by UV waves. So X-rays have a lower frequency. That is not true. X-rays travel faster in a vacuum. All EM waves travel at the same speed, the speed of light, so that's not true. X-rays do not show diffraction and interference effects. All waves show diffraction and interference effects. Using the same element, photoelectrons emitted using X-rays have greater maximum kinetic energy, while the X-rays have got greater energy, so therefore the photoelectrons will have greater maximum kinetic energy. So the answer is D. Question 5. Monochromatic light may be characterized by its speed, frequency and wavelengths. Which of the following quantities change when it passes from air to glass? Okay, so this is all about refraction. What happens when something passes from air to glass? So we have a beam of light coming to glass, changes direction. Why does it change direction? It changes direction because it slows down and bends towards the normal, and then when it comes out again it speeds up and turns away from the normal. So what changes? Speed changes, but also wavelength. Now we know these two are wrong because the frequency, for the frequency to change, what we would need is we would need to somehow at the boundary either put in an extra wave or take a wave cycle out. And by doing that, we're removing or adding energy, which contravenes the principle of conservation of energy. So these two are definitely not possible. Speed is equal to frequency times wavelength. We know that the speed is going to change. The frequency can't change, therefore the wavelength has to change. So it is B. Question 6. Monochromatic light of wavelength 490 nanometers falls normally on a diffraction grating that is this number of lines per meter. Which of the following is correct? So we know that the number of number of lines is 6 by 10 to the power 5 lines per meter, so that means that the slit spacing is going to be 1 over 6 by 10 to the 5 meters. So that gives me that the slit spacing is 1.67 by 10 to the minus 6. So that's our slit spacing. The equation again from my sheet is d sine of the angle is equal to n times the wavelength. Right, so the first statement they offer is they're saying the first order, so n equals 1, is observed at this angle of diffraction. So we can put that in. That is suggesting that the sine of the angle is equal to 1 multiplied by the wavelength, 490 times 10 to the minus 9, all divided by 1.67 by 10 to the minus 6. So I can put those numbers in and I will get an answer of, from the first order, the angle that I find is 17.06. So right away I see this one is correct. So at this point in a test I would just circle that one, move on. I can go back and check later. I'm going to check anyway. So I've got the second order observed at an angle of diffraction of 34. It's highly unlikely that's the case because not a linear relationship, but we can quickly check that. We're saying that the sine of the angle is equal to 2 times 490 times 10 to the minus 9 divided by 1.67 by 10 to the minus 6. And when I get that value, I've got an answer of 36 degrees. So this one is wrong. Then third and higher orders are not produced. That's suggesting that the angle would be greater than 90 degrees. So we can check that. Sine of the angle is equal to 3 times 490 times 10 to the minus 9 divided by 1.67 by 10 to the minus 6. So if I put that into my calculator, I get an answer of, for the third order, I get an angle of 62 degrees. So this is not true. So question 8. So question 8 is about diffraction. It says, a diagram above shows the first 4 orders, I beg your pardon, for a beam of monochromatic light incident on a diffraction grating. Slit separation is D. All the angles are small. Which one of the patterns is obtained when the grating is exchanged for one which has got a smaller slit separation? So it's D divided by 2. So the expression we're using from the equation sheet, D sine of the angle equals n times lambda. N is the order. This is the wavelength. That's the slit separation. So the sine of the angle is equal to n, the order times the wavelength divided by the slit spacing. So if I decrease the slit spacing, which is what they're proposing to do here, what that will do is it will increase this sine of the angle, so it will increase the angle, so the lines will be further apart. So if I decrease slit spacing, the lines end up further apart. So these two are closer, so those won't be correct. This one is the same, no change, so that's not correct. So the answer has to be D. Question 9. So question 9 says, interference maxima produced by a double source are observed at a distance of 1 meter from the sources. In which one of the following cases are the maxima closest together? So remember, this time we're talking about double slits, so we're using this equation. We've got the fringe spacing is equal to the wavelength times the distance to the screen divided by the slit separation. So we're told, first of all, we've got red light, wavelength 700 nanometers, and the sources are 4 millimeters apart. So that is, the wavelength is 700 by 10 to the minus 9 meters, and the slit spacing is 4 by 10 to the minus 3 meters. So I'm going to put that into the equation to work out the value for W. So that gives me W is equal to an answer of 1.75 by 10 to the minus 4 meters for the first one. That was the first one. So the second one, I've got sound waves. The wavelength is 20 millimeters, so that's 20 by 10 to the minus 3. From sources 50 millimeters apart, so S is 50 by 10 to the minus 3. So that's going to give me a width separation, which is 20 times 10 to the minus 3 divided by 50 by 10 to the minus 3, which is equal to 4. Sorry, I beg your pardon. 20 divided by 5 is 0.4 meters. Then the third one, we've got blue light. The wavelength is 450 nanometers. The sources are 2 millimeters apart. So again, I put that into the equation. I've got 450 by 10 to the minus 9 divided by 2 by 10 to the minus 3. So that gives me an answer of 2.25 by 10 to the minus 4 meters. And then finally, I've got surface water waves. The wavelength is 10 millimeters. Its sources are 200 millimeters apart. That means that the slit separation is, the fringe separation is 10 by 10 to the minus 3 divided by 200 by 10 to the minus 3, which gives me 1/20, or 5 by 10 to the minus 2 meters. So the answer is B, question 9. I beg your pardon, not B, this one, A. That looked odd. Okay, so the answer is A for this first one. It's 1.75 by 10 to the minus 4 compared to 2.25 by 10 to the minus 4. Now for speed, very quickly we should notice that for this one with the sound waves, B, and for the one with the surface water waves, D, because the wavelength is very large, and it's similar to the size of the source separation or the slit separation, I end up with fringe separations that are around about 1, or in this case 100th. These are large numbers here, whereas in this case there is a significant difference between the wavelength in both the red light and the blue light. There's a significant difference between the wavelength and the slit separation. The wavelength is very much smaller, which means I'm going to end up with a very much smaller answer. So if I was doing this in an exam, I would immediately eliminate B and D. I wouldn't even consider them. I'd probably just double check to make sure that my reasoning was correct in choosing between A and C. Okay, question 10. Light of wavelength is incident on a normal diffraction grating, and the adjacent lines are this distance apart. What is the angle between the second order maximum and the straight through position? So I'm looking at this angle. Remember, I've got D sine of the angle is equal to the order times the wavelengths. Okay, so we're told that the adjacent lines are 3 wavelengths apart. Beg your pardon, not the adjacent lines between the fringes, of course. The adjacent lines on the grating are 3 wavelengths apart. So I've got the sine of the angle is equal to lambda over d, so that gives me the sine of the angle is equal to n times the wavelength divided by 3 times the wavelength, so the sine of the angle is equal to n over 3. Okay, so I'm looking for between a second order maximum and a straight through position, so the sine of the angle is equal to 2/3, which means the angle is equal to 41.8 degrees. Answer C. Question 10. The diagram shows a microwave transmitter T which directs microwaves of length at 2 slits, typo there, S1 and S2 formed by metal plates. The microwaves that pass through the slits are detected by a receiver. Okay. When the receiver is moved from P to O, which is equidistant from S1 and S2, the signal received decreases from a maximum to the minimum. Which one of the following statements is a correct deduction from this observation? So they're saying that here we have maximum, so we have constructive interference, and here we've got minimum, which is destructive interference. So at this point we can say that the path length for 1 is equal to the path length for 2. There's no phase offset. Whereas we can say for this case, in this case, the path length for 1 is less than the path taken for 2. So there is a path difference here. Now for destructive interference, the waves have to destructively interfere. So that means that the distance from this distance, P1, P2, so P1 is from S1 to P, so S1 to P must, and I've got S2 to P, S2 to P. So S2 to P is greater than S1 to P. How much is it greater by that? It must be greater by a half a wavelength. So I've got P2P minus S1P is equal to a half a wavelength. The notation is a little bit different here, but we get the idea. So here we've got the path difference is equal to half a wavelength. If the path difference was a wavelength, that would be constructive interference. The path difference has to be half a wavelength for destructive interference. That, by the way, if this number A was true, this would be saying we had destructive interference at point O, which we didn't. We know we had constructive interference. So the answer is C. Question 11. Question 12. Got point sources of sound. The same frequency are placed at S1 and S2. When a sound detector is slowly moved along the line PQ, consecutive maxima of sound intensity are detected at W, the central position, and Y, and consecutive minima at X and Z. So here, this is a bright fringe. This is bright, this is dark, this is dark. So this is my constructive interference. And where it's dark, I've got destructive interference. Which one of the following is a correct expression for the wavelength of the sound? So what we can say is that we've got between S1 to X, to this point, and S1 to W, I don't know. So I don't know what the path difference is there. It could be very large, it could be some number, don't know. So to be able to work this out, what we need is we need to have a comparison between the path taken from one of the sources to a point compared to the other source to the same point. So we need to have something that has the second letter is the same. So this is not going to be useful, neither is this. So it's going to be one of these two. Now we're looking for the wavelength. So we're looking for constructive interference because we're saying the path difference is a multiple of the wavelength for constructive interference. So which one of these could it be? Well, at X we've got destructive interference, so it must be therefore D, because this is the one that is constructive interference. So for question 12, the answer is D. Question 13. In Young's double slit interference experiment, monochromatic light is placed behind a single slit, eliminates two narrow slits, and we see the pattern. Which one of the following decreases the separation of the fringes? Again, I'm going to use the equation from the formula sheet to help my reasoning. So I'm trying to reduce W. How can I do that? I can do that by reducing the wavelength, I can reduce the distance to the screen, or I can increase the slit separation. Those are my options. So what am I doing? I'm saying I'm increasing the width of the single slit. That's not going to affect this particular value for the fringe separation. I can decrease the separation of the double slit. So that means I would be decreasing S. So that would increase the fringe spacing. So that's not the right answer. Increase the distance between the double slits and the screen. So there I would be increasing D. And that would, so if I'm increasing D, I would again be increasing the separation of the fringes, so it's not going to be that one. And using monochromatic light of a higher frequency, so in this case I'm using a higher frequency. So if I increase the frequency, which means I've reduced the wavelength, and if I've reduced the wavelength, I've reduced the fringe separation, the answer is D. Question 14. Light of wavelength is incident normally on a diffraction grating, and the slit separation is 4 times the wavelength. What is the angle between the second order maximum and the third order maximum? So remember, the equation that I'm using is the slit separation times the sine of the angle is equal to the order times the wavelength. I know that the slit separation is 4 times wavelength, so that gives me that the sine of the angle is equal to n lambda over d, which equals n over 4 times the wavelength equals n over 4. So for the second order, n equals 2 gives me the sine of the angle is equal to 2 over 4, so that's a half. So the angle is equal to 30 degrees. And for the third order, n is equal to 3, which means the sine of the angle is equal to 3/4. So that means that the angle is equal to 48.6 degrees. Now, I'm not looking for the angle itself. It says, what is the angle between the second order? So this is that angle between the second order and the normal. This is between the third order and the normal. So what I need is I need to find the angle between them. So that's going to be equal to the angle for the third order, take away the angle for the second order. So the answer is going to be B. Question 15. Interference fringes produced by monochromatic light are viewed on a screen placed at distance D from a double slit system with slit separation S. The distance between the centers of 2 adjacent fringes is W. If both S and D are doubled, what is the new fringe separation? So again, I'm looking at the equation for my data constant sheet for this reasoning, and what I've been told is S has doubled and D has also doubled, so my new value for the distance is also doubled. So that gives me that the fringe spacing is going to be the wavelength times 2 times D divided by 2 times S, and the 2's cancel out. So I'm going to be left with, overall, no change. I have the same fringe separation. An arrow beam of monochromatic light falls on a diffraction grating normal incidence. The second order of the diffracted beam makes this angle. So I know I'm looking at the second order. Remember, this is my equation. And it's asking what is the highest order visible with this grating at this wavelength. So I don't know what the wavelength is, and I don't know what the slit separation is on the diffraction grating. But what I do know is that when n equals 2, the angle is equal to 45 degrees. So the sine of the angle is equal to n over d. Now, when n equals 2, the angle is equal to 45 degrees, which gives me 2 times the wavelength over the slit separation is equal to 0.707 or 1 over 2 times the wavelength divided by the slit separation is 1 over root 2. So dividing both sides by 2, I get the ratio of the wavelength to the slit separation is root 2 over 4, which is 0.354. Then what I can do is, I know that when I have the maximum order, that means that the angle is close to 90 degrees. So the maximum order is when that's 1, the sine of the angle is 1. So that gives me the maximum order is going to be 1 divided by this ratio. So that gives me n is equal to 4 over root 2. And that is equal to, maximum order is 2.82, but we can't have a fraction. We have to round this down, so that gives me the maximum order is 2. Now, question 17. Coherent monochromatic light of wavelengths emerges from the slits to form dark fringes at P, Q, R, and S. Which one of the following statements is true? When the distance d, the separation. Okay, so once again, we're looking at the double slit experiment equation to help our reasoning for this question. So the slit's separation is equal to the wavelength times the distance to the screen divided by the slit separation. So the first statement says when the distance d is increased, the separation of the fringes increases. That's true. So that could be our answer, and we could, if we were pressed for time, just circle D, move on. When the distance between x and y, so that's the slit separation, is increased, the separation of the fringes increases. Well, that's not true, because if I increase S, I'm going to decrease W, so that one's definitely false. When the width of the slit T is decreased, the separation of the fringes decreases. Well, that's to do with the single slit diffraction, nothing to do with the double slit interference pattern, so we can ignore that. There is a dark fringe at P, so these are all dark fringes, so this is destructive interference because the path difference is a multiple of the wavelength. That's not true, because that would be constructive interference if true. So if that one was true, it would be constructive interference, but it's not. It's destructive interference. So as we said right at the start, the answer is A. Monochromatic light of wavelength 590 nanometers is incident on a plane diffraction grating having these number of lines per meter. What is the highest order visible in this diffraction pattern? So we have, remember this equation, d times sine of the angle is equal to the order number times the wavelength, which gives me the order number times the wavelength divided by slit separation is equal to the sine of the angle. At maximum, sine of the angle is equal to 1, therefore n lambda over d equals 1. So we're looking for the highest order visible, and that's going to be highest order is equal to d divided by lambda. So d is equal to Well, we've got 4 by 10 to the power 5 lines per meter, so that's going to be 1 over 4 by 10 to the power 5, which is equal to 2.5 by 10 to the minus 6 meters. And then we have the wavelength, we're told is 590 nanometers, so that's equal to 590 by 10 to the minus 9, so that's 5.9 by 10 to the minus 7 meters. So what have I got if I do this? I've got 2.5 by 10 to the power of minus 6 divided by 5.9 by 10 to the power of minus 7 gives me an answer of the maximum order is 4.24. I need to round that down because I can't have a fraction of an order, so the answer is going to be 4, or C. Question 19. In a double slit arrangement, the fringe spacing when the wavelength is shown, the distance between the double slits is S, the distance between the slits in the plane or the screen is D. Again, we're going to use the equation to help our reasoning. And what are we told? Which of the following would the fringe spacing also be W? So we're going to put in these values. So we've got, in the first case, we've got 2 times lambda for the wavelength, the distance between the slits and the fringes is 2 times capital D, and distance between the slits is 2s. So that would give me, I've got 2 times lambda D over S, so that's going to be equal to 2 times the original value I had for W. So it's not this one. Take a look at the next one. We've got the new value for the fringe separation is 2 times the wavelength times 2 times the distance screen divided by 4 times the slit separation. So that will equal the original value. So I could choose now, right, just pick B, move on, and I'll just quickly check the others. So for C, I've got 2 times the wavelength times 4 times the distance divided by 2 times the slit separation before, so that gives me 4 times the original value, so that's not true, that one's not true. And then for D, I've got 4 times the wavelength times 2 times the distance of green divided by 2 times the slit separation, which again gives me 4 times the original, so that's not true, so the answer is B. Question 20. Using a diffraction grating monochromatic light, I know the wavelength is 500 nanometers, 5 by 10 to the minus 7 meters. Second order in direction of, it was found in the direction of 30 degrees. What is the number of lines per meter? So I've got my equation is from the equation sheet. I'm going to put that, reorder that for the slit separation, and then the number of lines is equal to 1 over D, so that's going to be give me sine of the angle divided by n times the wavelength. So the number of lines was equal to, well, we were told it was at 30 degrees when it was the second order, so that gives me a value, the number of lines is 5 by 10 to the 5 lines per meter. So the answer is D. By the way, if this sort of question comes up in an exam, be very careful. It can be a little bit sneaky with this, and they might have asked what is the number of lines per millimeter, because it's often quoted per millimeter. Just be careful that you double check what units they're looking at. Question 21. A double slit interference experiment is performed using a monochromatic light. The center of the observed pattern is a bright fringe. What is the path difference between 2 waves which interfere to give the third dark fringe from the center. Okay, so here we have a bright fringe, constructive interference, and again constructive interference, and again constructive interference. So that is with dark fringes in between. So what we're saying is that here, this is where path difference was 0 for the two sources with the central bright fringe, and here is where there's destructive interference. So the path difference for that, the next bright fringe must have been a wavelength. So the path difference between the center and the second bright fringe is 2 wavelengths, and this must be a further half a wavelength. So I get destructive interference. So overall, I've got 2.5 wavelengths. So the answer is C. In Young's double slit experiment, the fringe separating is S when the wavelength is lambda, the slip separation is W, the distance between the slits in the plane is D. Which one of the following would the fringe separation also be S? This is a nasty question, as Donald Trump might say, because what they've done here is, remember, the equation says W is equal to lambda D over S, and you have to remember S in this equation equals the slit separation, and W is the fringe separation. But they've swapped the symbols around. So they're saying in this case the slit separation is W and the fringe separation is F. So they've said that in the first case we've got S is equal to lambda D over W. Okay, that's what makes this question a little bit of a nasty question, easy to get mixed up. So let's think of these cases in turn. So for the second case, we've got the fringe separation is equal to the wavelength, which in this case is twice, times the distance, which is also twice D, divided by slit separation. That gives me 2 times lambda D over W, so that's equal to 2 times the original. That's for A, so that's not the case. Then for B, we've got 2 times the wavelength times 2 times the distance to the screen times 4 times the original slit separation. Those numbers all cancel out, so that one's going to be the same, and I can just jump in there and say, right, it's going to be B, but I can quickly check the others work. So we've got 2 times the wavelength times 4 times the distance divided by 2 times the slit separation to give me 4 times the original. And finally, so C is not correct, and then finally for D, I've got 4 times the wavelength times 2 times the distance divided by 2 times the slit separation, again giving me 4 times the original answer, so that's not correct. Okay, question 23 is about refraction. It says figures 1 and 2 each show a ray of light incident on a water air boundary, and we see the ray directions. Notice this one, we've got a light ray that's coming out of the water into air. And what we should always do in these questions is just put in our normal where the ray is meeting the boundary, just so that we can clearly discuss what is happening. Okay, so it says circle the letter below that corresponds to a direction which a ray cannot occur. What we have here is we've got a ray of light, and here we've got it bending towards the normal. Okay, so remember the little expression tagaga. So this is saying if we're towards, it bends towards the normal when we go from air to glass. the ray turns away from the normal when we go from glass to air. So here, and it's the same for water. So here we've got a ray of light that's coming out of the water. This should bend away from the normal. This should bend this way. So this one cannot be true. It cannot turn towards the normal. The second ray we see here, the ray B, this is showing reflection, and this cannot happen. And what we expect here is that the angle incident is equal to the angle of reflection, which seems to be the case. So B is possibly true. And then we've got on the other side, we've got a ray of light. Here we have it bending away from the normal, so that could be true. And again, we've got the angle of reflection is roughly equal to the angle of incidence, so that one looks okay. So the answer is A. Circle the letter below that corresponds to the direction of the faintest ray. So the faintest ray is where we have the reflection, but we are not approaching total internal reflection. So as the ray it turns up in this direction, it means that the incident angle is becoming bigger, the angle of refraction will become bigger, and eventually we will get total internal reflection. So the amount of light reflected increases as we increase this angle. This angle is much bigger than this angle. This incident angle is much bigger than this incident angle. So I would expect B to be brighter than D, but I would expect the refracted rays to always be brighter. So the answer here, I would suggest, would be D. Question 24. Young's two-slit interference pattern. So we're told that the red light has a wavelength of 7 by 10 to the minus 7 meters. We're told that the fringe spacing is 2 by 10 to the minus 3 meters. What separation would be observed in the same place if we used blue light? So if we had used blue light, which has a wavelength of 45 by 10 to the minus 4, so we've got 4.5 by 10 to the minus 6 meters, and the we're looking for the fringe spacing separation. Okay, so remember we're using the equation. The fringe spacing is equal to wavelength times the distance to the screen divided by the slit separation. So in the first case, the fringe separation, which was 2, was for a wavelength of 7 by 10 to the power of minus 7 times this distance to the screen divided by the slit separation. So that ratio D over S is equal to 2 by 10 to the power of minus 3 divided by 7 by 10 to the power of minus 7. So that gives me a value for that ratio of 2,857. Okay, now we're going to move to the bigger wavelengths. So we've now got 4.5 by 10 to the minus 6 times the same ratio. Everything else is stayed the same. So that gives me that the new fringe separation will be so that's in meters, and remember here it's in millimeters, so that's my value in meters times 1,000, which gives me 12. I think I've made a mistake. Let me just check my powers of 10 here. So I've got 3 divided by 7 to the minus 7, and that's then multiplied by Yeah, so I've caused myself some confusion there. That gives me an answer of roughly 12.8 millimeters. Now, I don't have this here. So this has caused me some confusion, and I looked at this answer B and I thought that looks like the right answer, except that I'm a power of 10 out. What might the problem be? So I've just gone back and looked at the question again, and it said the red light had a wavelength of 700 nanometers. And then it said the blue light had a wavelength, and here it's given me a wavelength of 4,500 nanometers. Now, a wavelength of 4,500 nanometers, that is an infrared wavelength. That's a very long wavelength. So large wavelength, low frequency, low energy. We know that the wavelength of blue light is less than the wavelength of red light. So what's gone wrong here? Why has it given me a wavelength number that's larger for blue light? The reason being, this is a typo. This should be written as 4.5 by 10 to the minus 7 meters. Now it makes sense, because now I've got 4.5 by 10 to the minus 7 times that ratio, which gives me an answer of 1.28 millimeters, answer B. Okay. Then question 25. The diagram represents an experimental arrangement used to produce interference fringes in Young's double slit experiment. The spacing of the fringes on the screen will increase in, so again we're going to use our equation to check our reasoning. So we've got, this is the equation. So the spacing of the fringes on the screen will increase. So what do I need to do to increase the spacing of the fringes? I need to increase the wavelength and or increase the distance to the screen, or decrease the separation between the slits. The width of the single slit, no effect. The distance XY is increased. If I increase that, that decreases the distance between the fringes, so that's not going to be any good. A light source of lower frequency means increased wavelength. So that's certainly a possibility, and if push for time, I just pick it. And then finally it says the distance between the single and double bonds, the single and the double slits is increased. Well, that's not in the equation. That has no effect. So the answer is C. Okay, that's the end of the multiple choice questions. Quite a nice situation with question 24 with the typo. You'll see that gave me a moment where I was looking at my answers thinking, this doesn't look right. If that happens, it's a really good opportunity actually to check your understanding of the topic. Is it because I've made a mistake in my calculation? Is it because actually in this case there was a mistake in the question? But it allowed me to go back and reason through what I've been reading. Okay,